recording and then share again. Okay. Okay, so generally we have this picture, we've been dealing with this picture, but we know we have an E versus K relationship that we must deal with. So what's the E versus K relationship behind this very simple picture here? We have, let's draw a few diagrams here to remind ourselves of what we were doing in solid state 1. So remember that we had this E versus K relation. Okay, let's put here one particular direction, for example, and then we had, sorry, what can I do? So so we have this kind of a relationship here. Okay, so remember that we always start with a quadratic. We need to do this. Okay, so we have this quadratic dependence here. Okay, and then we did dispersion did something like this. Okay, and right here, these things, right here at the edge, we had pi over a, and this is minus pi over a. Okay, and so this was the k equals to 0. Okay, and we move, and this was a dispersion relation. Okay, so this is the E versus K relation that we're talking about. And remember that the semiconductor is at t equals 0 is an insulator. So all this region here is filled with electrons. Okay, and then we have also a, okay, we have also, then we have a gap. Okay, so let me draw it here. So we have situation like this. Okay, so this would be the valence band. This is going to be the valence band here, and this is going to be the conduction band. Okay, so and this at t equals 0, this band is completely empty, and this is completely filled. And then we have our Fermi energy is going to be somewhere around here, right in the middle, smack in the middle for a pure semiconductor. So let's put here. Okay, so this is the scenario that we have, and we know that anything that's going to happen is going to happen in the vicinity of the Fermi level. Okay, so this is the gap we're talking about here. Okay, and if we heat up the system, okay, we're going to have now electrons that are going to make a transition between the edge, this edge here of the valence band, and they're going to move to the edge, to the lower edge of the conduction band. Okay, there are, you know, semiconductors, emblematic semiconductors that don't have, you know, the topmost value of the valence band aligned with the bottommost level in the conduction band. But generally, this is going to be the case. For example, this is going to be the case for gallium arsenide, gallium, okay, and germanium, and various and then other combinations that we saw, the gallium, aluminum, arsenide, okay. So these are generally the semiconductors that are referred to when you draw these diagrams, and I'll analyze what you're going to do with an heterostructure, okay, or a p-n junction, or, you know, the various other types of devices that you use in industry. Okay, generally then we focus on this piece here. Okay, so everything is going to happen close to the Fermi energy. So we're going to focus on this piece of the diagram. Okay. Yeah. Okay, on this small section of the, so, and that region of momentum, right? So we're going to focus on that. So any questions about this? This must be very familiar to you. And so we disregard all this, you know, deep into the Fermi sea, nothing's going on because the electrons have no places to make transitions, so they cannot absorb energy from external fields, they cannot be biased or anything. So everything is going to happen here. Okay, the scale, remember the scale of the thermal energy is going to be only very comparable to the gap energy for the, for example, germanium has the smallest gap among these semiconductors, but this is going to be less than 1 electron volt. But remember that the temperature scale, remember that KBT, here, KBT is going to be 1/40th of an electron volt. So it's going to be a fraction of this gap. And obviously, no electron is going to be able to save the energy scale that involves transferring an electron from down here up to the conduction band. Okay, so all these electrons are going to be inert. Okay, and all the action is going to happen very close to the Fermi energy. Okay,
Teacher,
so yes.
yes, and generally we saw another scheme uh, that says that, for instance, the valence band
Yes.
was like an inverted parabola that was
Yes.
just for silicon.
No, no, this is an inverted parabola, right? So that's one thing. That's what I'm going to draw next slide. Okay.
The
So this is an inverted parabola here, right? So we use the repeated zone scheme and we prolong this, right? So let me draw that so you have the full picture. Okay, so again you have this. So remember that the repeated zone scheme that you had, and let me prolong this here, and we can do this. Okay, so let's do this. Another color. So we have now. So I'm just So we have the same dispersion I drew before, but then we can repeat it. Remember that we repeat that this is the first brilliant zone, and then we draw the second brilliant zone. It goes like this, right? Okay, and then you can continue. You can continue on just repeating one zone after the other. So this would be the edge of the brilliant zone here. Okay, this ends in pi over a. So here we have the inverted parabola, and we can do the same for the conduction band. So the conduction band starts here, okay, and this is the first brilliant zone, and then you draw the second brilliant zone, okay. And you see that I draw in general, it can have a different parameters to the parabola corresponding uh, to the conduction band. Okay, so this is the scheme that I'm drawing here. So remember that in the previous view graph, I just emphasized that we were going to look in the vicinity of this guy here. Okay, this is the region I'm going to look. So generally in the textbooks, and all the papers you're going to see when you refer to the emblematic semiconductors, we're going to see just the drawing, okay, uh, just drawing a single axis, and then you are going to see red, okay, so you're going to see just this drawing here. You see, what happened with this? Ah, I forgot to translate this here. Okay, so you're going to see just this depiction. What's going on here and what's going on. Okay, so that's generally what you're going to see. So this is the inverted parabola and corresponding to the conduction. You still see the are you still seeing the board? No, we lost it.
No, no.
Wait a second. Wait a second. I was pushing something that I shouldn't. Push. Yeah. Okay. So this is going to be the conduction band. Okay, this is going to be the valence band, and this is going to be the conduction band. So generally, when we just draw the two-band picture that we saw before, this one here, we're just reflecting this very edge here, okay, this very edge here, and this very edge here, and we translate it in position. Okay, this will of course this is the k vector. Okay, but we translate those points. Let me erase this so it's not confusing. That's the k direction. This is the energy direction here. Okay, E versus K. But then you translate, you take these points, okay, and then you make this diagram here for a fixed K. Okay, the fixed K you're working on. Okay, so this will be the valence and the conduction band. Okay, but now in the x direction. Okay, this is another dimension that you don't put here. Maybe this dimension you can have in the perpendicular direction, perpendicular to the plane of the blackboard here, and this the direction would be. So this energy here is going to be precisely this energy here. Okay, this energy here, and this energy here is going to be this. Okay, is it clear? The relationship between the different diagrams in energy?
Yes.
Yes. Okay, so this is the scenario. This is why we focus on this edge, because everything we do, again, the Fermi energy is going to be around here, and that's where all the action is. So you always have to ask, when they show you a picture of the band structure or the relationship between E and K, the dispersion relation, where is the Fermi energy, so you can focus on that point and not, delude yourself looking at other places where there's no action going on related to when you bias your semiconductor, when you expose your semiconductor to external electric and magnetic fields, everything is going to happen in the vicinity of the Fermi energy. So this is the next question after you have the dispersion relation. The next question is where the Fermi energy is. Okay, where the mobile electrons, or the electrons that are going to be susceptible to external perturbations, where they are, where these electrons. Okay, so this is the full picture. Okay, so now let me draw a dispersion relation, which is maybe a little more detailed dispersion of what you see after either you calculate or you measure these dispersion relations in for a particular material. Okay, so let me just make one drawing here, and this is sort of a more realistic drawing where we're going to see what happens close to this edge. I'm going to call this the edge of the valence band and the edge of the conduction band. And this is sort of the shortest distance an electron in energy that an electron is going to have to travel in order to access the conduction band. This is precisely what we're describing here. Okay, so what happens without this? See here that we're just taking the parabolic approximation, but you know that if we go further off from the edge, we're not going to see parabolas. This is just the free electron approximation. Here, this is the free electron. So there's a very weak influence of the potential. So everything is sort of either parabolic here or parabolic on the other side. Free, almost free electron. Okay. So what's in reality what we're going to see in the experiment or in the a more detailed theory. So in principle, from the conduction band, we're going to see obviously around the edge is going to be very parabolic, but if we go off, it's going to go like this. Okay, so this would be the conduction band. Okay, and so we have only a parabolic, a good parabolic approximation if we are close here to okay to the edge. Okay, the same thing is going to happen now for the valence band. So let's draw the valence band from here, for example, and we're going to see now how this can happen. So in general, we're going to have now one band that can go like this, okay, and we can have another band that goes like this. Okay, this is very close to the edge again. And then finally, if we include the spin effects or the spin-orbit interaction, we're going to have another band like this. Okay, this is the picture that you're going to see in the books. You see that all these bands are locally parabolic around this edge, but then when you go farther, and this is the one of the axes, for example, the kx axis and the energy. Okay, and this is what happened, for example, for the emblematic case of gallium arsenide, okay, which is maybe the most popular semiconductor to make devices. Okay, so here you're going to have now we're going to have this will be named in general the gamma point. Okay, this is going to they each have names. So this is called gamma 7. This is called gamma 8. Okay, this refers to this particular point here. Okay, this point here. So these two bands are degenerate there, so it's the same point. And then this is going to be here. This is going to be the gamma 6. Okay, this is all notation from group theory. Okay, which is not beyond the scope of this course. But these are called, this is the names that are given to these points, okay? And then you know the curvature, and this we saw at the beginning of the course, and then we basically forgot about it, that this is going to be the effective mass related to the effective mass of the conduction band, okay? And then this is going to be now, we're going to have a low curvature here, which is related to a heavy mass. Remember that the inverse of the effective mass is proportional to the second derivative of the energy with respect to K. So when you have a low curvature, you have a high mass. And when you have a high curvature, you have a low mass. Okay, so this is going to be a heavy hole, effective mass. Okay, and notice that you have a high curvature close to the band edge. So this is going to correspond to a light hole, effective mass. And then this is called the split off band, okay, or the spin orbit band, okay, and this is going to have its own effective mass. So you see that now this the structure of the valence band is much richer, okay. These are going to be these orbitals are going to be made of px and py and pz like, okay, like orbitals. Okay, this is because of the structure the structure of, the valence band, which is going to be made from these kinds of orbitals. Okay, remember, for example, that the structure of gallium is going to be the argon, okay, argon structure deep into the levels, and then beyond the argon structure, we're going to have a 3d10, a 4s2, and a 4p1. Okay, so again, these levels are going to be hybridizing. Okay, so you see that the topmost filled level is going to be p-like. Okay, so these are referring to these orbitals, and the next one, okay, are going to be the five. Actually, yes, the five S's. Okay, so this is going to be S-like. Get S-like. Okay, so this is going to be an S-type orbital, and these are going to be P-type orbitals here. Okay, so so you see that then this very simplified picture is actually containing various effective masses of holes, and those and just one type of an effective mass in the conduction band. Okay, so you see actually, and this you will see in every text you see. I mean, this is basically the structure, the dispersion relation that you will be working with if you're designing a device. Okay, so it's really important to understand at least this structure here. If we're not going to include any spin effects, the structure associated with this two band structure. Okay, or three band structure that you're going to have. Okay, any questions about this? Okay, so you see we can have two types of masses for the holes that are going to be left after we make these transitions. Either very heavy electrons that are going to be difficult to accelerate in an external electric field because they have, this is going to be a mass that's going to be larger than the bare mass of the electron, and this actually is going to be smaller. Okay, and this is all. Why do we have heavy and light type carriers? It's because of the interference effects between the electrons and the lattice potential. Okay, so that's the interplay. Here, this can be more or less similar to M0 or the S-type dispersion relation. Okay, so that's sort of the broad scenario we have for the types of carriers that the electron.
Teacher.
Yes.
So we will have another band in a higher energy that corresponds to the 5p.
Right. So if you go further up here, you have empty bands that that involve the higher p and the higher d orbitals and so on. Okay. And below this, you will have some other structure associated with this. these observations. But those bands are going to be totally inert. I mean, there's no electron that's going to be reaching, that's going to be occupying those bands, okay, except for in the language of solids 2, virtual excitations that the system may have, okay? And even the effects of those bands can be included in what I'm going to tell you about in the following, okay? But generally, those bands have very weak effects of what's going on close to the Fermi energy, okay? That's why we focus on the effects of these bands in the very vicinity, okay, of the Fermi level. That's going to be somewhere here, okay? So yes,
Okay.
this structure continues up, just like the structure of gallium, of the gallium arsenide unit, okay, unit cell. Okay, okay. So how do we address the basic structure of the dispersion relation in the vicinity of the Fermi level? Okay, so so let's begin with that. So what do we know is the equation that's governing? Okay, so let me just make a title. How do we describe electrons in vicinity of EF? Okay, so we know that in spite of the efforts of many people to go beyond, the Schrödinger equation is a guiding equation here. I'm going to put here the bare electron mass, and so this is the kinetic energy, and we will have a periodic potential. Okay, this is the periodic. To right potential, and this is the classical form of the kinetic energy, or the and you know that here we have to make the first quantization, which is going to be substituting the classical P value. You turn it into an operator, and this is the first quantization. Okay, the first quantization procedure. Okay, and then this you apply to the wave function, and here we'll add an index associated with a band, okay, and the k corresponding to that particular band, and then this depends on the position, okay, and then we have the eigenvalues, okay, which I will denote like this, the eigenvalues associated with that particular band, and the k, and then we have the wave function, okay. Okay, so this is our Schrödinger equation, okay, and so this is the differential equation that's going to be governing the electrons either moving in the valence band or in the conduction band. Okay, on the other hand, we know that the Bloch discovered in the context of condensed matter physics, solid state physics, Bloch discovered that the form of this wave function is going to be a generalization of the plane wave. Okay, so this is going to be the plane wave, but then it's multiplied by a periodic function which depends on the position. So this is going to be periodic, okay, in lattice potential. Okay, so if we know that the solution has to have this form, okay, then we can just derive now an equation which governs the shape of this periodic function, okay? So this is what we're going to address, and this is called the KP method, okay, KP method, which lends itself very easily to deriving the physics around these points here, okay? And this is actually what we want to know, the physics around this edge here and the physics around this edge here, okay? So we know that this is going to be the maximum, either the maximum of a band or the minimum of a band, and both of those are going to be quadratic behaviors, but they can have different effective masses. So we want to describe what this effective mass is going to be, and these effective masses are going to be in the vicinity of this point. Okay, so this is a technique that's completely made in order to address that problem specifically. Okay. Okay, so we're going to substitute now this form here into the Schrödinger equation, and we're going to see what's going to happen. Okay, so so we embrace the first quantization. Let me choose black. Okay, so we embrace the first quantization, which is substituting the momentum operator by its first quantized form. Here we have the bare mass, okay, nabla squared, okay, plus the potential, okay, and apply this to the ik dot r u n k, okay. This depends here. Now they're always going to put the dependencies, but I put it once at least, so that you know. And here again, e to the ik dot r u n k. Okay, so here this is nabla. So we're going to this is going to differentiate. This has an R dependence. This has an R dependence. I'm not going to do all the details of the taking the derivatives. Okay, you can see that you're applying the chain rule here. This is going to be two derivatives. So I'm going to have a derivative with respect to the exponential, then a derivative with respect to this function that also depends on R. So I don't think you'll have any difficulty to follow through the chain rule. You know enough about this. So 2 or 3 steps. Okay. If you have any difficulties, we can discuss. If you have any problems deriving this, but after doing this procedure, without any approximations, just following your nose with the algebra and the derivatives, you will get p squared, and I'm writing again a compact form of this operator here. So you get to m0, and this only applied. You see that the exponential, always the derivative of the exponential will generate the exponential itself, multiplied by some prefactors related to k, but you will have the exponential on both sides that can be cancelled. Okay, because here you cannot cancel it because you have this operation here on the exponential. Okay, but after you do all the derivatives, then you will be left with a global prefactor of the exponential on this side and a global prefactor with the exponential, which you can cancel. So you will only be left with an equation for the u. Okay, so here we have u and k plus h k and 0, so p applied, okay, to u and k. Okay, and here we of course we leave all the derivatives of u indicated. So this is one of the derivatives that we can have. This applied directly to the u will leave this derivative of the u because this is the differential equation we end up having to solve. Okay, and then you have terms like this. Okay, so we have a quadratic dependence on k, and then you have the potential. Okay, and on the other side of the equation, you'll have your E and K, okay, U and K. Okay, so this is now there's a dot product here. Okay, so this is the equation we have to address now. And this term here is precisely why we call this KP theory, because you end up with this strange looking term, KP name. Okay, not mane. Mane is the hair of the horse. Okay, so name. Okay, so this is what gives the method its name. Okay. Notice here that you have these two terms here. This one and this one here. Okay, so we can separate now our equation and rewrite it like this. So we have p squared over 2m0. This is always the bare mass of the electron. And then we will have the potential, okay? And here we will have our Kp term, this, okay? All being applied to the U and K. And here, this term here, this quadratic term, I'll pass to the other side. So we can have then the eigenvalues, okay? Minus h squared, k squared over 2m0 applied to U. Okay, so this is the same equation we took as common function over which this operator now operates in the Schrödinger equation. And remember, these are always the, we have the P, this is just a compact way of writing the first quantized form of the operator. So this is the differential equation, okay? And so here, this is a trivial term. Remember that we already know K, because K is going to be the K associated in the vicinity of this point. Okay, so this is going to be the K around this point. So this is fixed already when you're looking, okay, so you know this, this guy, known. This is the bare mass of the electron. So all this term, this is just a trivial parameter that we have in this equation. So it's not involved at all in the solution of the problem. Here we have the same. Remember, this is the crystal momentum, okay, or the momentum associated that you refer to when you talking about the Brillouin zone. Okay, while this is an operator here, so you have to distinguish between this momentum, hk is a momentum, and this momentum, which is the operator. Okay, so that's something that's very confusing when you see this theory for the first time. The distinction between P and HK. Okay, one is an operator, the other one is just a parameter of the equation. Okay, is this clear? Okay, so now, as always with these perturbation problems, we're going to treat this in perturbations. Remember that this K is going to be very close to this point. We're just describing what happens right at the edge where we're going to be extracting electrons and receiving electrons on the other side, on the other band. So K, okay, K is a small, let me write it in with another ink. So it's highlighted here. K is a small. And of course, you know that this is a common feature of all perturbative treatments, that you need a small parameter in terms of which to make an expansion. So K is small, so this term is going to be small, okay? And this is going to be the unperturbed Hamiltonian. Okay, so this we should know what's going to happen right at k equals to 0. Okay, so this approach assumes we know what happens. Okay, that is what we know how to solve at k equals to 0. Okay, k equals to 0. So we know that physics, and that physics, and we either know what's going to happen, what happens there, either because it's a very simple model to solve, okay, or because we can apply other tools like, for example, group theory, which tells us what the form of the functions are going to be in that vicinity, or we have a friend with a big computer that knows how to compute that point, okay, and we want to know what happens in the vicinity of that point using this procedure, okay? So we're going to call this Hamiltonian, this one, H0, okay? And so we have this problem here, H0 plus now this parameter here, okay? Okay, and this is going to be the generic problem. This is going to be the phrasing of the problem we're going to have. Remember that we always have this, the eigenvalue of this equation referred to this value of the element. Okay, very good. So this is going to be the perturbation. This is the, let's see, perturbation. Okay, and this is a small parameter. And this we're going to use as a perturbation of the problem. And we're going to assume that we know the solution to this problem in the various ways I told you before. N0, U0. This is solved beforehand. Okay, so we know these functions here. Okay, and actually we in the what are called the high symmetry points of the dispersion relation, we actually can solve even by hand these expressions here. For example, for semiconductors are insulators, so it's very easy to know actually these functions in the vicinity of this band edge are going to be almost exactly the hydrogenic functions associated with the atoms that constitute the solids, okay? So let me just make that remark. So this is going to be very close, okay, to hydrogenic functions. And I will mention that before we end the class. Okay, of gallium, for example. Okay, so we know what these functions are in at the edge. So we know that these are going to be the energies associated with hydrogenic functions, and we know that we have a table for those in every textbook you care to look. Okay, so basically this is going to be the hydrogenic functions. Okay, hydrogenic functions. Okay, corresponding of course to the filling that I mentioned before for gallium specifically, for example. Okay. Okay, so we know these solutions here, and we want to see what the effects of this term is going to do to those hydrogenic functions. Okay, so how do we approach this problem? So we look in our quantum 2 course. I think is where you see this. So you see the time independent perturbation theory. So you look into your bag of tricks, okay? This is something that you really must remember at least, and then look up in your uh, in your previous courses, and see that this is going to be a very basic tool in order to consider these kinds of problems. So you look up in your basic quantum mechanics text of the undergrad, and you look up this time independent theory, and you'll see that you get these expressions here, which is a very simple expression for E and K minus H squared over 2m0. Okay, this is what's on this side of the equation. Okay, is going to be equal to, okay, as a first approximation, of course, n0, which is the k equals to 0 value. Okay, this is the energy k equals to 0 value. And then we're going to have a first term, okay, which is going to be proportional to k. And this is going to be the matrix element between n, p, okay, this is the operator, and sorry, I'll just put the same thing. So this is going to be the diagonal element of this operator here, okay, and remember this is going to be un0. So this we know beforehand because we solved this equation. We solved this equation before. Do you know how to calculate this matrix element? And I'm going to write this integral in a second. Okay, and then the next term in this series is going to be this guy here. Now this sum is going to be over all the n primes different from n, okay, which is a common n here we have on this side. And then we have k and the matrix element p n prime. This is going to go squared. Okay. Again, you derive this in your quantum mechanics 2 class. I get the two students that we have here with from a nano that might not be familiar with this formula, but it's really not very difficult to derive. And then you have higher order terms here. Okay, so this either you know how to derive, or you take it from you take it as a basic result from time-independent perturbation theory. Okay. Okay, so you have this formula here, and you see that you can calculate everything on this side. We know these energies from, again, the previous, having solved this problem here, this eigenvalue problem. Okay, you know how to calculate these matrix elements. Let me write this. This we can call also Pn and prime. Okay, so Pn and prime is going to be done by calculating this integral here of un0 conjugated, the operator p, and n prime 0. Okay, so you calculate this integral and you plug it into your perturbation theory. We know these energies here, and the k here is going to be a parameter. Okay, so this is going to be the eigen value that we want to determine through this theory. So you see that here we have the full now solution, okay, approximate solution to the problem. And here you see that we have a quadratic dependence on k. So clearly this is going to be a correction to the mass. Okay, here we're going to have the basic, the unperturbed value of the bare electron mass. This is the bare electron. There. Okay, and then we're going to get other contributions to the k squared term, which is going to modify this this guy here. Okay, perturbation theory, okay, perturbation theory also gives an expression for the wave function, the approximate value of the wave function, u and k in the vicinity, but I won't write it here because we won't use it. Okay, and also this theory assumes that these wave functions here that we know from the previous problem are an orthonormal set. So we have that these wave functions obey this relationship here. In prime 0 are a delta function in prime. Okay, orthonormal set. Okay, very good. So we know this, and here is a full solution of the problem. So how do we extract the effective masses from here? So let me write a simplified version of this this equation. Okay, so we have that the energy, okay, the eigenvalue of the equation is going to be approximated in the first approximation by the bare energy, the energy at the band edge, plus this hk squared over 2m0, okay? Then if you calculate this term here, you will find that this term is going to be 0. You have to do this integral right at the band edge. This is going to be 0. In physical terms, this is quite expected because you know your dispersion is going to be strictly quadratic around this point. So there should be no linear term in k. Remember, this is the k-axis. Okay, so this term should be 0. This term is 0. So we get only this term, and then we get this correction here to the second order. Okay, so we get this term that's coming from the left-hand side, and then we have a term like this. A squared, and then we have this matrix element where n is different from n prime, and then we have this energy decombination. Okay, and then you can, systematically include higher order corrections here that are going to be associated with the deformations. Remember that if you go far away from the small k regime, then you get these other non-quadratic contributions to the dispersion. But strictly very close to here, you only have quadratic corrections, which is what is expressed in the expansion. So you see that, knowing about these perturbation methods is very useful because then you're going to have here terms of order k cubed, okay, and terms of order k to the fourth, which are describing the deformations of the band structure away from the k equals to 0 case, okay? Okay, very good. But now we have these two terms that are quadratic. So if we join these two terms here, we're going to have some reference point here, en0, and then we can extract from here the h squared over 2, okay? And here then we have 1 over m0 plus, and then you have the pn and prime square interaction, and you have m0 squared here, and then you have 1 over en0 minus en prime 0. Okay, and this is multiplied by h squared. So here you have the first term, h squared k squared over 2m0 is this term here. Okay, and then we have this correction here. Here I'm making an assumption. Okay, this is going to be I'm going to assume that the bands are isotropic. Bands are isotropic. This means that if I rotate this drawing if I rotate this drawing here around the energy axis, okay, so we go to, for example, to the kx direction, okay, and the kz direction, this is going to be isotropic. This is going to be the same picture. So this is that has cylindrical symmetry with respect to the energy axis. Okay, and of course I'll write to you the more general expression if we don't make those assumptions, because crystals are not isotropic. So we can make a more sophisticated expression, which shows the dependence in the different k directions. Okay, so for now we have this expression here, and you see that if we yes.
Maybe I am wrong, but when you take the common factor, the 2 is not missing a 2 inside the.
Yeah, there's a 2 here, right?
Okay.
Okay, so yeah, because there's no 2 here. Okay, good. So you're following the math. Okay, so here we now try to express this term here in terms of a 2m effective mass k squared. Okay, so you see that here we have this feature of k squared. We have this h over 2. Okay, outside here, and the rest of this expression is going to be expressed in terms of an effective mass. So here we're going to see that this whole expression is going to be 1 over the effective mass. So this is how we obtain the effective masses due to this correction here, due to this perturbation theory. Okay, so this is very nice. Let's see. I don't think it's worthwhile to express it, but note that this difference, and this is a feature that I should point out, En0, M prime 0, this is going to be the band index, okay, at the 0 point. So where this, what is this expression? So this is going to be the difference between these 2 points. This is the band N, and this is going to be the band N prime, okay? So this difference is going to be the gap. Okay, so that's very easy. So this term is going to look like 2bn n prime squared over m0 squared. This is the bare mass, and this is going to be the gap energy. Okay, so this is and then we're going to have 1 over m0, and this whole thing is, and I think I'm not missing anything, right? So this is going to be 1 over the effective mass. Okay, so remember that the effective mass is going to depend on the gap. If the gap is larger, okay, the effective mass is going to be larger also. Okay, so the effective mass of the carriers is going to depend on the gap of the material, and it's going to depend on these integrals here. And this is going to be the bare, so this is going to be a correction to the bare mass energy. Correction to bare mass. So this is a very, very simple and useful expression in order to see what's going to happen. This is basically coupling between bands, coupling between bands. Okay, and it tells you what the interference effects with the lattice potential is going to be, and how it modifies the curvature, okay, of this dispersion versus this dispersion and so on. Okay?
Teacher,
yes?
For the expression of the effective mass,
yes,
this is valid for all the carriers, for electrons and holes?
No, so now we have to make this. This would be we can make two versions of this expansion. We can either see how the effective mass of this guy is going to be affected by this guy, okay? Because we're eliminating one of the bands and seeing what the effects of that band are on this one, or we can do it the other direction. We can see the curvature of this band due to the effects of this band, okay? So this is sort of the here. So this is the one band approach. Okay, and we're going to see now the two band approach. So we're going to obtain both effective masses. Here we obtain one effective mass, eliminating the other band. Okay, this is the simplest. So we eliminate the effect of n prime. So here we see this is going to be one band, either the conduction or the valence band, either. Okay, so we fix one of them and include the effect of the other one here. Okay, or this could be n prime, and then this would be n here, and so we would be addressing the conduction band or the valence band depending on the orderings of what I put here and what I put here. Okay, so this is the one band approach. Okay, we won't have time to address that problem. I can give you the notes on how to address both bands, but I just wanted to, in the single band picture, where we already are obtaining either the mass of the valence and the conduction bands, okay, or the conduction bands. What happens in the anisotropic case? So remember, this picture we saw in at the very beginning of the course. Remember that we have a one-dimensional solid, okay? So you have this arrangement of the atoms, and you have this lattice parameter, okay? So here you will have electrons propagating in this direction. Just see this periodic potential. But what happens in a general solid, even in a two-dimensional solid, you have a regular structure, but then you have two directions at least, okay? Okay, and so if electrons are propagating in this direction, they will see this lattice parameter, this periodic potential. But this periodic potential changes as I change the direction of the electron. So if I propagate now an electron in this direction, it will see this lattice parameter here. This I may call. Okay, so if I propagate an electron in this direction, it sees this A prime. So now it's going to propagate perpendicular to these set of planes here. Okay, so the interference effects are going to vary depending on the direction. Here, again, if this is a square lattice, we will see the same dispersion as I see in the x direction, for example, this x and y direction. Okay, so you see that the interference effects are going to depend on direction. So this is in general going to be an isotropic effective mass. Okay, and this is completely taken into account by this dot product that you see here. This is a k with respect to this. So we have to calculate this. This is going to be a vector because this is a vector. Okay, and here it takes into account the directionality of this integral, and it's going to be built onto the k dependent. So what's the general expression we're going to obtain if we take care of those integrals? Then we're going to have that En, so it produces I strain if I use it. So we're going to have that the dispersion as a function of k minus the reference energy that from the equation that we know how to solve is going to have a generic structure So we're going to have a tensor here, okay? And instead of this being a simple quadratic expression, it's going to be a bilinear expression, okay? Like this. And from here, we can write this in terms of the effective mass by extracting an h squared over 2 term here, alpha beta. And this is then going to be an effective mass tensor, which will come out from that expression by solving the integral, okay? And then k alpha, k beta. Okay, so now we have a tensor, okay, which contains diagonal terms, okay? Okay, this will be the 1, 1, 2, 2, 3, 3 term, and then we're going to have off diagonal terms. I'm just going to put 1, which is the 1, 3 term, which will depend on the particular direction, okay, that the electron is propagating in the lattice. And this is going to be the generic form of the mass tensor, okay? Okay, so basically this is the idea I wanted to convey to you of how to address the problem now of the dispersion relation of the semiconductor, that in order for you to make specific calculations and to feed the scenario that we had before, the simple scenario. This is actually the valence band is going to have a structure. So you're going to have different carriers associated with the holes that we had in the valence band and the electrons that we had in the conduction band. The conduction band is typically going to be very simple. So for example, N-type semiconductors are going to be very easily described because most of the carriers are here. But if you have P-type semiconductors, then you have a much more rich type, 2 types of carriers, 3 types of carriers, depending on whether you consider spin effects. And you're going to have to include that in the design of your material. The good thing is that this is a very well developed area. There's lots of parametrizations you can find in the literature regarding these effective masses. And this is the way they obtain this by, in a similar way to the tight binding approximation where you parameterize this. Essentially, we're really not calculating these parameters by doing the integrals, but obtaining these parameters by fitting these with the more sophisticated methods coming from DFT and ab initio approaches. So we calculate those integrals from there, and then you can use this as inputs to your problem, okay? And then do your theory with very simple expressions like these for the effective masses you use for your theory, okay? This is basically it, what I wanted to tell you. If you need, okay, if you if you're interested, for example, in the two-band picture, okay, which is just going to be a matrix, a matrix treatment to this problem. We will have the spaces of both bands included, okay, or including spin effects. Okay, then I can give you references in order for you to see how this treatment follows. Okay, but I think this is enough, at least for the scope of the current course. Okay. So, do you have any questions about this? Is this scenario clear enough for you? I'm open to questions. Okay, so if you have no questions, okay, as I said, this is the final class. Okay, You still have some sessions with Berna, with some lab sessions. I hope those are going well. Okay, you have a lab session tomorrow, for example. I understand the Berna records the lab sessions and then discusses them in the times that are assigned to this course. Okay, so what I promised for you this week is a schedule for seminars. Okay, remember the seminars are going to be the week 13, 14, 15, 16, and 17. Okay. Of course, we will have sessions at the regular hours, sessions at regular hours. Okay, but we have to make for additional sessions. We have only 2 sessions that week, so we have to agree on additional sessions because we have seminars from 20 to 30 minutes. Okay, and you have groups of 2, so you have to share the time. Those who are have topics groups of 2, so you have to accommodate for both of you to share the seminar. And we have sessions like this. We can accommodate 2 or 3 seminars in the time allotted to the course. Okay, but we must decide upon other days. So please discuss among yourselves which sessions we can have either Monday, okay, Monday or Tuesday, at what times we can meet. That week, in principle, there are no more classes. Okay, so if we can have a session Monday, Tuesday, Wednesday, and Thursday at most, if we need, then we must decide at what times we're going to meet on these 2 days. Okay, so name some representative and tell me, write to me what hours we can meet on these 2 days for the seminars. And I will announce the order. Okay, we'll announce. Order. Okay, this I do okay, by lottery. Okay, so very good. Any questions about this? No. Okay, so you're all set. Okay, so, remember. Okay, you have some of you have homework pending, so please send it to me as soon as possible. I have to have the grades by the end of that week, the week of the seminars. So, and of course, I will push Berna to finish grading the homework that has already been handed in. Okay, have it well organized, but he has been preparing the lab session, so I guess he hasn't had time to grade. Okay, I think we almost all the students did very well in the midterm, so I'm happy that I think you understand the material. Okay, so that's it for this session then.
Okay.
Okay.
Professor, one question.
Yes.
Me and Kevin we are sharing the same topic since he asked me if we can give it together. So we also have to give the presentation in 20 to 30 minutes. So we have to give it each one 20 to 30 minutes.
No, all the topics, almost all the topics are being shared. So just prepare a single presentation and distribute between you the content. Okay.
Okay. Thank
Okay.
you.
Okay. Any other question? Okay, very good. So see you then by email, or if you need any a session before that, a tutoring session, for example, we have some question about your topics, about your seminar, then please write me, and then we can have either a Zoom session with a subgroup, or okay, or you can ask me things over the email, and I'll answer. Okay, very good. Okay, so see you then. Bye bye.
Thank you. See you.
See you.
See you.
So.